Hi, I'm Brooklyn Aviles, and this is my Physics 2211 Lab 1 constant velocity. In order to do the lab, we first need to understand the fundamental physics principles behind it. This includes Newton's first law: an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an outside force. We also have the momentum principle, or Newton's second law: the force of an object is equal to the change in its momentum. The momentum principle can be rearranged to find the velocity update and the position update equation, which we will use in the GlowScript code. The purpose of the lab is to observe constant velocity. This means that there is no force acting on the object that would cause it to speed up, slow down, or change direction. We would then use the momentum principle to model the constant velocity on GlowScript. Since momentum is conserved, our position versus time graph would have a linear slope, and our velocity versus time graph would show a constant non-zero line. From this experiment, we were able to see that the velocity has a relatively constant velocity. Our position versus time graph from the tracker had an r-squared coefficient of 0.9949. This means that our graph was linear. A linear position versus time graph shows a constant velocity, since position is changing by an equal amount each time. As a result, we are able to see that our tracker follows the momentum principle. We first need to define the system. We define the system as the block, and the surroundings as everything else, which include the track and the table. Based on the free body diagram from the left, we define the net force to be 0. We can see that after the initial push, there are no external factors acting on the block other than the normal force and the force of gravity, which are equal and opposites of each other, so F net is equal to 0. Our initial conditions include that after the initial push, the net force on the system is 0, and the velocity of the system is the average velocity of the tracker. Our experimental design included pushing the object from rest and recording it in the positive x direction. In the tracker, we then plotted the center of mass for each time point, which allowed us to create a table with the positions at each time. We then used the initial position and the final position of the tracker over the total time to find the average velocity, shown on the left, which was implemented into the GlowScript code. Here we have our tracker video where we were then able to create the position versus time graph shown on the right, which shows a linear slope. The first image shows our initial velocity and position vectors for the rest of the code. The second image shows our position update equation, where we are updating the position by multiplying the velocity by the change in time to get our updated position. We can see that from the code, we were able to get a linear position versus time graph and a constant non-zero velocity versus time graph, where we are then able to see the motion on the right. Based on the graph, we can see that our tracker position was not as linear as the GlowScript position. We used the average velocity of the tracker video for the GlowScript code. This means that the GlowScript position versus time graph shows what the tracker graph would look like if it was truly non-constant. No, if it was truly constant velocity, unlike in the graph where the tracker has a slight curve in the center. Sources of error include inaccurate and rush point mass placement. When placing the point mass dots, there is a chance that as the video kept going that I did not place them as accurately. This could have caused the curve in the middle of the graph that shows a little bit of acceleration in the position versus time graph. Imperfections of the track and object. Since this is not a perfectly controlled experiment, it is possible for there to be a friction force present, which would cause the velocity to be non-constant and therefore messing up our position versus time graph. If the positive and negative x-axes were interchanged, the slopes of the tracker and GlowScript would be negative. This would mean that our constant velocities will also be negative, since the object would be traveling in the negative direction. We cannot directly determine how many forces are present to get a net zero force. We know that there is a force of gravity and a normal force that are equal and opposites of each other, and that there would be a friction force applied in the negative x-axis. But we do not know exactly how many forces are actually being applied to the object. In conclusion, the position versus time graph shows a fairly linear slope, therefore showing a constant velocity. As a result, we can see that the experiment upholds Newton's first law, since we can see that the object in motion will remain in motion unless acted upon by an outside force. Additionally, we can see that the momentum principle is upheld, since the velocity is unchanging, so the net force is 0 and there is no acceleration. So the initial velocity is equal to the final velocity.